A standard deck is shuffled, and a single card is drawn, looked at, and then put back in the deck. If X is the number of times that a diamond is drawn when this experiment is performed 48 times, find the probability that X, the number of diamonds, is less than or equal to 19. So notice that we're interested in just one outcome, either it's diamonds or not, and we're performing the same experiment over and over and over again. And the probabilities aren't changing because we're putting our card back into the deck. So this is a binomial random variable. At least that's what the X is, a binomial random variable. Doing something 48 times, what are the chances of getting a diamond? Well, the diamond is 1 out of the 4 suits. Or you could say 13 out of the 52 cards in the deck are diamonds, but that simplifies to 1/4 as well, or 0.25. Now, because we've got a binomial random variable here, we can figure out its mean and its standard deviation. And the reason we want to do that is because we're going to answer this question using normal approximation. So what is the mean for a binomial random variable? Well, you take the number of times you're running the experiment and you multiply it by the probability of the outcome that you're interested in. So for us, 48 trials and chance of getting a diamond 1/4. So the mean for this experiment is going to be 12. How about the standard deviation? Well, that's the square root of the variance, which is n times p times 1 minus p. So we get the square root of 48 times 1/4 times 1 minus 1/4, which is 3/4. Now, 48 times 1/4, we just found out, is 12. 12 times 3 is 36, divided by 4 is 9. So square root of 9, or 3, is our standard deviation. So what we can do is we can say something like, let y be a normal random variable with the same mean and same standard deviation. And this y will be a good approximation for our x, which I'll remind you is a binomial random variable. Okay, so we got a normal that's a good approximation for our discrete random variable that we'd like to study. Now, let's talk about the probability we want. We want, oops, wrong button, but we want the probability that x is less than or equal to 19, that we have at most 19 diamonds. Okay, but this probability is not easy to calculate, so what we're going to do is we're going to change it so it's a probability in terms of y, our good approximation. And the way we do that is we draw ourselves a mock histogram. So 12 is the mean, and then, well, we'll make it roughly bell-shaped. And the picture doesn't have to be super exact. It's, for our purposes, just to understand what areas should be shaded and not. So I'm just going to go all the way up to 19. So 13, 14, 15, 16, 17, 18, 19, 20. And we could go on the other side, 11 and 10, things like that, but we don't need that information. So what would I shade? What represents this sort of probability? Any value of x that is 19 or less. So we're going to shade in all of these rectangles. All of them. Even the ones that are a little lower that we haven't even drawn. So we would just keep going. Okay? But what we're interested in is, where does the area start and stop being shaded? Well, it stops being shaded halfway between the 19, the last shaded thing, and 20, the first unshaded thing. So 19.5, that's where our area starts and stops, and that's how we can switch to a probability in terms of our normal random variable. So it'll be y less than. It's always less than or greater than. We don't deal with equals, because normal random variables are continuous random variables. But instead of 19 or anything like that, it's 19.5 because that's where the shading stopped. So that's where our area under the normal curve should also stop. Right? So we use the mock histogram, and now we've changed from a discrete random variable that we were interested in to a continuous one. And now, well, how do we answer this new question? Well, it's a non-standard normal random variable, so what we're going to do is we're going to change it to be in terms of the standard normal, because this has a chart we can easily look things up. How do we do that? You take the value you're comparing y to, you subtract off the mean, which we already worked out is 12, you divide by the standard deviation, which we worked out was 3. So the probability we want is the same as the probability that the standard normal z is less than 2.5. But this I can quickly look up in our table of z-scores. We'll have to scroll down a little bit. 2.5, and then the hundredths digit is 0, so 0.9938. And that's it. That's the probability we want. 0.9938. So it's very nearly a 100% guarantee that if I do this process 48 times, I will get 19 or less diamonds. Okay? We establish a probability in terms of a discrete random variable. We trade it for one in terms of a continuous normal random variable. And then we trade that for a probability we can look up in terms of the standard normal random variable. And there's our answer, 0.9938.